All right. So 3G, we are all about powers, polynomials and circles, and there's some types of graphs here that you need to know. So before I do those ones, just to give you a bit of a recap, we know our y equals x squared graph is our basic parabola that looks like that, right? What happens if I switch the x and the y? So it's x equals y squared. Does anyone want to guess or know? Yeah. It turns the parabola like that. Okay, so but we don't normally like to have an x equals equation. We like to have the y by itself. So if I take that equation and I get rid of the squared by square rooting the x, and when you square root, you get a plus or a minus. So technically this equation and that equation, they're the same thing. I've square rooted. But the plus or minus breaks that sideways parabola into two parts. If it just said the positive square root of x, it's the top part. If it was the negative square root of x, it's the bottom part. The two parts together make the whole sideways parabola. Okay, so the reason I did that was because that's our very first box. Y equals square root of x is the positive half or the top part of that sideways parabola. If it had a negative in front of it, it would be the one underneath. The y equals x cubed graph, we've practiced that last year in our option topic, the cubic graph. That's the basic one where you have the bend on the origin, and all cubics have that kind of shape. Although we are going to do some other modifications. Last year we learned how to move them sideways and up and down. We're also going to add in another type of bend that you'll see in the examples in a minute. X to the power of 4 is the same kind of shape as a parabola, but it's a little bit squarer on the bottom because when you have a number that is less than 1, so say I had a half, when I do a half squared, it actually gets smaller. A half squared is a quarter. Okay, so any of those smaller numbers that are less than 1, when you square it, it becomes a quarter. If you do the power of 4, it gets even smaller again. So what is happening here is the small values are even smaller down the bottom there. But once you get past 1, so 2 for example, 2 to the power of 4, we're up to 16. 3 to the power of 4, we're getting some really, really big numbers, so it starts getting really, really steep, really, really fast. But it does have that basic parabola shape. And anything with an even power, so x to the power of 6, x to the power of 8, x to the power of 10, if we ever did anything that unusual, it would have that same basic parabola shape, but the larger the power is, the more it's going to have that kind of square bottom on it and be super, super steep. Yeah? Next one, our circle. The circle on the origin is x squared plus y squared is equal to r squared. We just need to know what the radius is from that number on the end. So if it was a x squared plus y squared equals 9, we would square root the 9, which means the radius is 3. Okay? From that, we could rearrange the formula. If I got the y squared by itself, I would get r squared minus x squared. And then, to get rid of the squared on the y, I would square root this side, which means, again, you're going to get a plus or a minus option when you square root it. When you have the positive option, which is this one, that's your positive square root, it is going to be the upper half of your circle. If you have the negative in front of the square root, that's going to be the lower half of your circle. There are also sideways semicircles. Do you remember those ones from year 10 too? We did talk about them super briefly in year 10. They are the ones that have the equations that it's x equals either plus or minus square root of r squared minus y squared. You're switching the x and the y around again. Okay? The positive version is the right-hand side of the semicircle. The negative version is the left-hand side of your semicircle. All right, so there's a few little things that you should be familiar with. Then a bit more information down here. we are pretty good, we should be pretty good at sketching parabolas, right? We're good at parabolas. We've done lots of lessons on doing parabolas, and we are somewhat familiar with cubics. We know our basic cubic, but not all cubics have to be in the y equals x to the power of 3, and that's it, kind of formula. If you had a formula like this, y equals, I'm completely making this up here, x cubed plus 2x squared minus 5x plus 7, that is also a cubic, because the highest power of x there is a power of 3, which makes it a cubic, okay? It is going to have that cubic shape, but it's going to have a few more intercepts, and I made that up, so it's probably going to be really nasty intercepts for that one. But if you can factorize it, and none of you do extension math. The extension math people, they have to learn how to factorize stuff like that, okay? But for you, yours are going to be factorized for you. Once it is factorized, it will be something like this. When you have a parabola, back to parabolas again, you know it factorizes to 2 brackets, and you get 2 intercepts from that. So a cubic, power of 3, is going to have 3 brackets. And guess what? You're going to have 3 intercepts that come from those brackets. Yeah? And there's a bit of notation in here. Don't freak out about the Greek letters. The alpha, the beta, and the gamma, they are the symbols that are used to represent what we call the roots or the zeros of, which are the points of the x-intercepts on your graph. Okay, so that's kind of, you know how in geometry we also use Greek letters, we also use that in for roots of equations. So you'll be seeing that a little bit more often, the more of this kind of stuff that we do. So they will normally just be numbers. Alpha, beta, gamma, they will be numbers. What about the number in front here? The A, that would just be a number. What would that do to the cubic? What would an A in front of a parabola do? If it was a parabola?
Wider.
Yeah. So it just makes it steeper. So, well, assuming it's larger than 1, it would make it steeper. That's right. If it was less than 1, you're right, it would make it narrower or like so wider. So it does say in here that the steps to drawing these is that you should draw up a table of values. There is a shortcut around that. I'm going to do at least the first one with the table of values, but we'll see how we feel whether you want me to show you the shortcut or not. If the curve meets the axis at x equals a without crossing it, then the x-axis is a tangent to the curve at x equals, actually I think that's an alpha, not an a, x equals alpha. What that means is that some of the zeros, the x-intercepts that we're going to be finding, most of them cross straight through the axes. But there are some that come down and touch the axes, and I say they bounce. That's what I call them. They bounce back off and they go back the same way, which means their tangent is, they're making a tangent to the axes there. But you're going to see that in the examples, so I'll explain that a bit more when we get up to it. All right, parabolas we know. Cubics, we're like, yeah, all right, we can do this, cubics. But it goes even further than that. We can call any type of thing that can be expanded out like this is known as a polynomial. And that starts all the way down from a straight line. So something like y equals 2x plus 4, it's a line, but it's also a type of polynomial. It's technically what we would call a degree 1 polynomial because the highest power of x is a power of 1. A quadratic is a degree 2 polynomial. A cubic is a power of 3 polynomial. And then it can keep going. So the word polynomial just encompasses any kind of power as high as I want it to go that's in that kind of form. And if I can factorize it up, I can get the zeros from the equation. So we just did 1, 2, 3. We did 3 in the last one for the cubic. This would be adding on an extra one if I had a power of 4. And anytime you add a power, it adds an extra bracket. And all that creates is yet another intercept on your x-axis. Okay? And again, it says draw a table of values if you want to do that, which I'm going to show you. All right, here we go. Question 1. Sketch the graph of y equals the square root of 1 minus x. Now, thinking about the table of graphs that I just showed you, it's kind of like that top left-hand side one, square root of, well, we just had square root of x. The minus 1 is going to shift it slightly. A few lessons ago, you learnt about domain and range. Remember that? And we learnt that if we have square roots and fractions, that's where we start having values that don't exist. So a fraction, for example, this is not the fraction. If you have a fraction, whatever is on the bottom of that fraction, so like that, 1 over x, whatever's on the bottom of that fraction cannot be equal to 0 because you can never divide by 0. So the domain for an equation like that one would be that x cannot be equal to 0. It can be everything else, it just can't be 0. What about square roots? Do you remember what you learnt about square roots? For domain? Yes? It can't be a negative, that's right. So I'm going to use that here. I know that whatever is underneath there, the x minus 1, it has to be greater than or equal to 0 because it can't be negative. I can't square root a negative, it will never work. Okay, so that tells me that x must be greater than or equal to 1. So the tip in the last part was we're going to draw up a table of values because we're new to drawing these kinds of things. So we're going to do it with a table of values, but you might find that after doing a few of them, you may be able to do it without. So x and y. I'm going to start with x equals 1 because that's the lowest value that I just worked out that I can have. So x equals 1, and I'm going to do a few more from that. 2, 3, and 4. Okay, so putting them into my equation up there, I have the square root of 1 minus 1, which is 0. Good. Square root of 2 minus 1 is 1. And now we need some decimals after that. Square root of 3 minus 1, that's root 2, which is approximately 1.4. Square root of 3 would be the next one, which is about 1.7. So for our sketch, I'm going to do it semi-accurately since we haven't drawn many of these before. We're going to have 1, 2, 3, 4 along the x-axis, and we're going to have 1 and 2 going up the y-axis. So starting with x equals 1, I get y equals 0, so it's starting on the line there. At x equals 2, it's y equals 1. X equals 3 is 1.4. Well, that might be a bit high. Make that a bit lower. X equals 4 is 1.7. And we're getting that sideways parabola shape. Yeah? If you were going to do it without the table, the most important thing is that you find where that vertex is going to be first, because that tells you where you're starting from. And then you could just either in your head just do a few values, so have a few values, so you've got a few dots on there, and then as long as you know what kind of shape it's going to be, you join it up. Question 2, sketch the graph of y equals x minus 2 in brackets cubed. Okay, so our basic shape of y equals x cubed is our cubic that comes down and does its little ziggy-zag thing. Okay, if you put a number on the end, so x cubed is, don't write this is just me thinking on the page here. If you go y equals x cubed plus 1, what does that do to a cubic? It moves everything up 1. Good. What happens when you put it in brackets? It moves everything sideways which way, left or right? Yes, for that one it's going to go to the right. It's going to go to that little, that where it's usually at the origin, the bend part, is going to be over at positive 2. Okay, so let's mark that on our diagram. So 1, 2. That's where my point of inflection is its technical name, is right there. Do you want a table of values, or have we done enough of these last year that we can do it without the table of values?
Do one.
Do one with the table of values, all right. Okay, so in the table of values, we're going to put a few things on either side of that point of inflection. So the 2 is where the important part is, that point of inflection. I'll do a couple of values smaller, and it's important to include 0 even though it was conveniently the second one down. Why would I make sure I include 0 though? What's important about it? That's the y-intercept, which is always a feature you want to show of any graph, isn't it? Okay, so 0 is always a good one to make sure you include. 3 and 4. All right, so if we sub in 0, what do you get? Can you use your calculator? It's going to be 0 minus 2, so it's minus 2 cubed, which is negative 8. All right, then sub in 1. What do you get? Negative 1. Good. Sub in 2. Go, Gabby. Good. Sub in 3. Yep. And then 8. Were you ahead of me? You already did this. Oh, just then. Oh, good on you. Okay, so remember that these are sketches. They don't have to be super accurate. But if I show on here, negative 1 can be about there, and negative 8 is going to be way down here. So at 0, negative 8, there's going to be a dot there. And at 1, negative 1, there's going to be a dot there. Go on the other side of my point of inflection. So at 3 and 4, we will have 1 and a positive 8 up there. So 3 is at 1, 4 is at positive 8. And then try to make sure you show that lovely cubic bend. As expected, it's just like the normal cubic graph, gone 2 spaces over to the right. Yes?
Like in your question, could you just have the point of intersection?
Yeah.
Or do you need a y-intercept?
So if I was doing this without the table, as long as I could work out where that point of inflection is, so I go, my point of inflection is at 2, mark that on there. It also happens to be my x-intercept, which is really good. Okay, and as long as I show my y-intercept, which is negative 8, they would be the 2 key features that you must show. The only other time that, you know how there are some questions that go, also show me an extra point when x is equal to 1. If it said that, then you would do that and you go, all right, here's my point, x is equal to 1, and that's 1 comma negative 1. Show your extra point on there. Okay, but every good graph must show your x-intercept and your y-intercept. And as long as you've shown that and you've got the basic shape of the graph right, you've done it, right? Yes? Question 3. Sketch the graph of y equals negative 2x to the power of 4. So the x to the power of the 4 is the slightly square-based parabola shape. What's the minus 2 in front of it going to do? Make it steeper, taller, yes. What about the minus part? Yeah, flip it upside down. Okay, so should we do our table? Since we're being really good here and doing tables, because the thing told us to do tables. X and Y. Where is the center of this graph? Where's the vertex? 0, so let's put 0 in the middle. Minus 1, minus 2, 1 and 2. Okay, so subbing in, we have minus 2 bracket, minus 2 to the power of 4 makes negative 32. The minus 2 to the power of 4 is 16, but then timesing it by the negative again makes it negative 32. When you do negative 1, you get negative 2 here. 0 is 0. Am I doing this too fast? You guys okay with this? It makes sense? All right, subbing in 1, it's negative 2 again, and subbing in 2 is negative 32. Again, that's a lot of detail. Main thing is to show where is the vertex. Okay, my vertex is at the origin here. And because that is also, it's the x and the y-intercept, we should show at least one other point to show that we've worked out the steepness. So let's show here, that's going to be the point 1. I might even do negative 1. There we go, and that will be at negative 2 down here. So make it a bit square on the bottom and then coming up really steep. Yes? All good with that? Question 4. These are the good ones. Sketch the graph of y equals, and we have 3 brackets times together there, which means this is a cubic of the new fun kind. Now, first thing you want to do is look at each of those brackets. And again, you're comparing this to parabolas. If this was a parabola, you'd be using those brackets to find the x-intercepts. And we're going to do that for the cubic. We're going to use null factor for a cubic to find this, we call them the zeros. So I'm going to write down here, I'm finding the zeros, which is another name for the x-intercepts. And from the first bracket, we would get x is equal to minus 2. Wouldn't we? Yes? From the second bracket, I would get x is equal to positive 3. From the next bracket, I would get x is equal to, excellent. Okay, now we're going to do this one the proper way because it said draw a table of values. And if you want to, question 4, I'll do it without the table. 5, sorry, the next one. All right, so if we follow instructions, which we should always follow instructions, to draw the table of values it wants, you want to have each of those 3 values that I've just found plus a value in between each one because you want to see whether the curve's above or below when it's in between those sections. Okay, so I'm going to leave a gap and then I'm going to have my smallest value, which is minus 5. Leave a gap, then I'm going to have my next value, which is minus 2. Leave a gap, my next value is 3. And then a gap on the, oh, I didn't leave a gap. Go back here. So that's going to be minus 2, that's going to be 3, and I need another one on the end. Okay, so I've got a gap in between each one of my zeros and they're in increasing order. Okay, so I want to test something lower than minus 5. So the obvious choice I think is minus 6. I want to check something between minus 5 and minus 2. So how about minus 3? Between minus 2 and 3, pick 0 because that's your y-intercept. Okay, so we want 0. And then something larger than 3, we want 4. Okay, so if you're ready to do some number crunching, you would get your calculator out and you would start typing in bracket. You're going minus 6 plus 2 bracket bracket minus 6 minus 3 bracket bracket minus 6 plus 5 bracket equals. So the first one is negative 36. Then you would go through and do it all for minus 5. But what's going to happen if you put minus 5 in? 0. Okay, because that's one of our zeros. What other ones are our zeros? So the minus 2 should also be 0, and the 3 should also be 0. I'm going to tell you the other ones, if that's all right, or do you want to calculate? All right, so the next one, if you put in minus 3, that should be 12. When you put in 0, it is negative 30. And if you put in 4, it is 54. Who wants to draw a graph to scale that goes to 54? Not I. So we're not going to have a scale on our y-axis, okay? What we want from this is we want to know when we have negative numbers in here, it means that our curve is going to be below the x-axis. Okay, so these negative ones, there's a negative one there, a negative one there. The graph is going to be below the x-axis. When you have positive values, so there and there, your graph is going to be above the x-axis. Okay, so let's draw this. Okay, so I'm going to have spaces on the x-axis just so it doesn't look completely ridiculous. On the x-axis, I have minus 1, minus 2, minus 3, minus 4, minus 5, 1, 2, 3, 4. All right, so the zeros were at minus 2, minus 5, and a positive 3. Okay, so using the table at minus 6, which I haven't even shown, but that just indicates anything to the left of this minus 5 here. Anything on that side of it is going to start below the axis. So it's going to start down here like that. It's going to be coming up to the minus 5. Then it's positive between minus 5 and minus 2. So it's going to come up and be positive and land back down again at the next 0. Then it's negative again between -2 and 3. So it's going to come down and back up again to the next one. And then it's positive again, so it's heading up into very high values after that. And you can see, like, remember the basic cubic comes down and does its little bend and goes down. It still has come down, but it does a little squiggle before it keeps going down. Important things to know is that where these things turn around should be okay. Should be approximately in the middle. And you should always label the y-intercept, which is down here at -30. We worked that out in the table. That's why I included the 0. What is the shortcut if I don't want to take all that time to fill in a massive table? All you really need to know is where the y-intercept is. Okay, so if you knew the y-intercept is down here, you would have to figure out the rest of the graph is going to be going through everything. It's much faster than filling in a big table. Yeah? Does that make sense? All right, let's do another one. Question 5, because this one has same but extra little thing in it, that lovely little power of 2 that's on it. This is still a cubic because this being squared means I have 2, I have an x squared here times another one there, that's still a power of 3, an x to the power of 3 in that. The zeros still come from the brackets. From the first bracket, I get x equals 1. From the second bracket, I get x equals -2, but put a lovely little arrow to that and write the word double. That one is a double. When we have these kind of ones, which is what we did in the last question, call that's a single 0, which are the ones that go straight through, that goes through that point and goes from positive to negative, or negative to positive, goes through the Cartesian point. When it's a double, it's special. A double will come down to that 0 and bounce off it and head back up the way that it came. So if it's coming down from the top, it'll come bounce, back up positive again. If it's coming from below, it'll come up, bounce, and go back down again. So that's what a double will do. If we are doing this without the table, are we brave enough to do that? Okay. If we're doing it without the table, I need to know the y-intercept. Where is that going to be? You're subbing in x equals 0. So we go when x equals 0, you would get, and put it in your calculator. Here we go. So we're going to have minus bracket 0 minus 1 bracket 0 plus 2 bracket squared is 4. So there's my y-intercept. Oh, I thought you had a question. No, you're good. Okay. Here we go, straight to the graph. Putting my zeros on there first. I have -1, -2, and +1. That's as much as I need. So -2 is my 0 that's going to bounce. And then my other 0 is at +1. 1. Okay, so the y-intercept is at 4, which I'm going to approximately put here. So I know my graph has to come from the 4, roughly in between. It's going to be coming down through the 4 and through the single 0, which is the 1. Yes? Then on the other side, it's going to come around and it's going to bounce off the -2. The double bounces. No, so not necessarily. But just because that's the intercept doesn't mean that's the highest point. The highest point is usually in between this. Yeah? Okay, get the idea? Let's do another one. Because this one, look at this one. That is a degree. How many degrees this is?
5.
5. So you have 2 here, and another 1. This is a degree 5 polynomial. If you were to expand that out, it would have 6 terms. But anyway, we don't have to expand it. Each one of those brackets there is going to give us a 0. So the zeros are, from the first bracket, x equals 1. Keep going, my pen. Oh dear. All right.
Yeah.
What do we get? X equals 1, x equals minus 2, and x equals 3. We have doubles at both the minus 2 and the 3. So you're going to have 2 points where it's going to bounce. Anyone go and find the y-intercept? Very good. So if x equals 0, y equals 36, you're just putting that into there. The short way to do that without all the brackets is just use the numbers on the end. It'd be minus 1 times 2 squared times minus 3 squared, and then it's all negative in front of that. Yeah, you can get rid of all the zeros. Okay, drawing it. We've got one. Oh, seriously, again. To bring my charger down here. Oh. Okay, at minus 2, then 1, then 3. They're the zeros. There, and there. The y-intercept was at 36, and there's nowhere near going to be to scale, but that will be somewhere up here, 36. So my graph has a single, which means it's going to pass through the 1. So it's going to come down and pass through the 1, come back up, bounce off the 3. Then it's going to come around the top here and bounce off the minus 2. What a great graph. Yeah?
It goes back down.
Because it had to bounce. Because it was a square. It had a square and it had to bounce. And you guys have used some Desmos. So remember that you can also be putting these things into Desmos if you want to have a bit of a play with changing the powers. And what do you think, just for fun, oh, you haven't used it yet? What do you think happened? I haven't done anything with a power of 3. What do you think would happen if I had a bracket that had a power of 3 on it? It will go through, but it will do a cubic bend going through it. So odd powers, so you single in your power of 3, they go through. The power of 1 just goes through normally. 3 does a cubic bend through. And your even, all of your even powers, so if you ever got anything as massive as a power of 4 or a power of 6, they all bounce. Yeah, your even powers bounce. Okay, all right, let's finish. We're nearly done. Question 7. This is an easy one. Yep. All right. Sketch x squared plus y squared equals 64. That is a circle. What is the radius? Yes, radius equals 8. So showing the radius and having the center on the origin is the most important thing, but try not to let your circle look too square. Snorted. 8, 8, negative 8, and negative 8. That's it. That's all you have to show. Question 8. Sketch the graph of y equals the square root of 16 minus x squared. What type of graph is that? I'm about to write it. What is it? Starts with S because I've written the S. Semicircle. And what is the radius of the semicircle? 4, so square root of 16. Is it going to be the semicircle above or below? Above, because it's positive. So there is my semicircle above, and it's negative 4, 4, 4. Just make sure you show those values and that it looks like a semicircle. Question 9. Sketch the negative square root. Oh, I still had answers in here from last time. Sketch the negative square root of 25 minus x squared. So that is also a semicircle. That's right, and it'll be underneath. So radius is? That's right. We're getting faster now, aren't we? There we go. Oh, that was not a good semicircle. I better do that again. So -5, -5, and 5. Question 10. Find the equation of a circle with a radius of 6 and a centre of 0, 0. We know if it's a circle, it's going to be x squared plus y squared equals the radius squared, and the radius is 6, so it is 6 squared. It says expanded form there. The only thing I could possibly do to expand that would be to say that 6 squared is 36. There's not really anything to expand. All right, question 11. Find the equation of a semicircle with a radius of 8 and centre 0, 0. What do I not really know about this semicircle? Yeah. If it's a bubble below. Okay. So assuming that it's in the y equals form, it's going to be square root of the radius squared, which is 8. So 8 squared minus x squared. But because it could be the above or the below, put a plus or minus in front of it. You're right. Which is plus or minus 64 minus x squared. All right, I think we finally made it to the end. Done, done.